Good morning. Today, I'd like to talk about what's called the twin paradox, although, as you'll probably guess, it's not really a paradox at all. This will let me talk a little bit about momentarily co-moving reference frames and a common misapprehension that people have about special relativity. So, to begin with, I'm going to have two individuals, twin brother and sister, Jim and Jane. They're standing right next to each other. I'm going to assume that they are at rest with respect to an inertial frame in a minute, but the apparent paradox is this. Jane moves away from Jim in some fashion or the other. You'll remember that moving clocks run slow, so when Jane stops at this position, her clock will have lost some time relative to Jim's clock. Then Jane turns around and goes back to where Jim is in some manner or the other. Since Jane has to move, her clock is still running slow relative to Jim's. So Jim will say, when Jane returns, that her clock is behind his. The apparent paradox is when people say, well, let's say that Jane is regarded as being at rest and it's Jim that moved backwards. On return, Jim's clock ought to be running slow relative to Jane's, and this is a contradiction, a paradox. In view of everything we've been through already, you can already see the problems with this. If I ask Jim if he ever changed direction or not, Jim, being at rest with respect to an inertial system, is going to say, what do you mean change direction? I didn't even move. Jane, on the other hand, traveled out in this direction some distance or the other. She may have done this at a constant speed or maybe different speeds at different points along the journey, but at some point she had to turn around and go back. The answer to this question is no. The answer to that question is yes. The situation is not symmetrical. In view of all the things we've talked about already, this should be enough to convince you that there is no paradox here, because one of the people is at rest with respect to a certain inertial frame, and the other isn't at rest with respect to any inertial frame all the way through the journey. The amount of nonsense that people talk in describing this situation is astounding. If you consult even some respectable books, they'll tell you very strange sounding things, which are, well, beta sigma when you get right down to it. Imagine the standard setup, as we've been calling it. O bar moves with speed v in what is colloquially called to the right relative to the O system. We have figured out that the t-bar axis shows up in the space-time diagram of O as the graph of the equation x equals vt, and we figured out that the x-bar axis is the graph of t equals vx. Those two equations are the same, except t and x have been interchanged. That means that these two lines, the t-bar axis and the x-bar axis, are reflections of each other across the line t equal x. Additionally, that means that this angle and this angle must be the same. This is how the time and x-bar axis of a moving reference frame will appear in the space-time diagram of O if an individual moves with constant speed and constant direction with respect to the O system, then the world line of that individual in the space-time diagram of the O system would look something like that. We are assuming that Euclidean geometry is true. For every point not on a straight line, there is exactly one straight line through that point parallel to the given line. So in particular, there's going to be a parallel line that passes through the origin. I'll call this angle phi. I could draw in more parallel lines if I wanted. Thinking of how we transform from one coordinate system to another, these are lines that are parallel to the t-bar axis. These are lines that have constant x-bar. But on the other hand, since I know this angle phi, I can draw in some other axes also. Because of the comments that we made previously, if I draw in a straight line that makes the same angle with the x-axis as this line made with the t-axis, this could be interpreted as the x-bar axis of some inertial frame. And then, just like with the other one, I can draw in parallel lines. In this way, if I have an individual moving at a constant speed and a constant direction relative to O, we can literally construct an inertial reference frame in which that object is at rest. This is an important point. We're going to generalize it a little bit here. Over the years, I've read any number of popular science books and articles about relativity. And one of the things that I see constantly, which is really funny, is the thought that special relativity can't deal with acceleration. You have to do full general relativity for that. A theory of physics that can't handle acceleration would, I guess, to use technical language, be a rotten theory of physics. In the space-time diagram, if the world line of an individual is a straight line, that represents straight line uniform speed motion. Therefore, if I have something like this, which is curved, this must represent motion that is accelerated with respect to O. Let's think about this for a minute. I'm going to select some point P along the world line. I'm going to think about the tangent line. Even though we've been doing all this strange stuff, this is a nice unbroken curve with no sharp edges or anything, so it's got to have a nice tangent line. If I remain close to point P in the space-time diagram, then the world line looks very much like the tangent line. At point P, the individual is going to be at rest with respect to an inertial frame in which this tangent line is parallel to the t-bar axis. Those are some lines that are parallel to the time axis of the frame of reference in which the individual at point P is momentarily at rest. I say momentarily because as you travel away from or go into the past from point P, the world line no longer looks much like the tangent line. By making the angle between that first set of lines that I drew in and the t-axis the same as the angle between this second set of lines I drew in and the x-axis, this is the phi angle from a moment ago, I can construct an inertial frame of reference which, at and very close to point P by making this angle and that angle the same, I have constructed an inertial reference frame. Right at point P, the individual traveling along this world line is at rest with respect to this inertial reference frame that we've constructed. Of course, just a little while later, it will be at rest with respect to some other inertial frame. But what we're going to do is we're basically going to use calculus 2 ideas. We're going to chop the world line up into such small pieces that I can imagine that the piece is more or less a straight line segment. Then I'll construct the frame of reference in which the individual is at rest on that interval. Any calculations that I need doing, I'll do using that inertial frame of reference and the one I started with. Then we add up all the contributions and take some sort of integral. Such a setup is called a momentarily co-moving reference frame at P, or we'll sometimes just say MCRF at P. Sometimes people are lazy and leave the at P off. We'll have to be careful not to do that. The previous work that we've done says that according to O, the moving clock must be running slow. If delta tau I, the chunk of proper time that goes with piece number I along the world line, is going to be radical 1 minus the speed on chunk number I squared times the amount of time that has passed according to O. That should be, of course, delta t number I. In a development that will come as a surprise to nobody who had Calc 2, we add up all these contributions, we take the limit as all of the delta ti's tend to 0. The total elapsed proper time is going to be the integral from the starting t value to the ending t value of 1 minus the speed squared raised to the 1/2 power. And notice the speed need not be a constant here. In fact, the interesting case happens when it isn't. Let's return to our friends Jim and Jane. They both start off at the origin, initially at rest. Then Jane begins moving in this manner. Jane's x-coordinate is going to be 0.999 times 1 minus cosine of t, where t can go from 0 to 2 pi. I want to write in some representative t numbers so that we get a feel for what's going on. I'll go through one entire cycle of the cosine function. I'll use the range from 0 to 2 pi. At t equals 0, x is 0 because Jane is located at the origin. At t equal pi, x is 1.998. Once I reach that, I begin moving back towards the origin again. When t is equal to 2 pi, x will work out to be 0. We will have gone through one complete cycle of this cosine graph. The amount of t that has passed is t started off at 0, ended at 2 pi, about 6.28. 6.28 years if we're measuring our distances in light years and our times in years. What I'd like to calculate is how much time passed for Jane during her trip that started here, went out to the place that has the label x equal 1.998 light years, and then turned around and came back, ending up at rest at the same place she started at. To do this, I'm going to need to know the speed. The derivative of x with respect to t is 0.999 times sine of t. That number is sometimes positive and sometimes negative, depending on what t is. The speed would be the absolute value of 0.999 sine t if one wanted to be picky about it. But on the other hand, in my formula, it's the square of the speed. So even though the speed needs to be positive, and dx dt could be positive or negative, when I square, any negative sign goes away, and it doesn't make any difference. T, the coordinate time, the time is measured by the coordinate system of O, goes from 0 to 2 pi. So that's going to be my limits of integration. I have to integrate radical 1 minus speed squared with respect to t. I'll do the integral on my calculator. It turns out that when Jane gets back to the starting point, she's going to claim that 4.015 some odd years has passed, while Jim is going to measure that about 6.28 years have passed. Special relativity has no problem with dealing with accelerated individuals. Accelerated frames of reference, that's a different story, and we'll have to talk about that another time. Until then, I hope everybody has a good day. I'll talk to you again soon.